Welcome everyone to week 4 of our uh, lecture series of our course here. I just wanted to take a look at the schedule real quick before we start. This is halfway through, so this is our midpoint in the course. This is lecture 13 out of 26. So we're halfway there, everyone. We've covered modeling and solving models, and the next few lectures will be about thinking about those models in other ways and seeing kind of neat applications of alternate ways to look at these models and ways to perturb them. So for tomorrow, I want you to read either section 3.1 or 3.2. The content is the same, they just look at different examples. There's one theorem that has a slight difference, which is, of course, the important theorem. And there's one of the reading quiz questions uses that version of the theorem from section 3.1. So if you read 3.2, you're going to want to look at that theorem in 3.1. In fact, I would recommend everyone to look at, I forget, let me see if I can find the theorems. Just look at them. You don't necessarily need to understand exactly how we got there, but theorem 3.2 and theorem uh, oh, that's too far. Should be on this page. Where did it go? Oh, there it is. 3.2 and 3.9. Those two theorems are they're actually equivalent, but they have a slightly different original model that they're applied to. And so it'd be good to look at both of those. And then we'll expand on those topics, either 3.1 or 3.2, in 4.1 and 4.2. Duality is my favorite part of this course. I think it's incredibly neat. So look forward to that, I guess. So yeah, homework 4 should not be particularly difficult. It's not as long as homework 3 was. So hopefully we can get that done without too much trouble. All right, so we've talked about that. Let's get into the content for today. And I've got to find where my here we go. So we're going to talk about redundant constraints and degenerate solutions. So we've solved linear programs in the last couple classes. We put them in standard quality form, we put them in canonical form, we put them in tableaus, and we solved those tableaus for optimal solutions by hand. and we found initial feasible solutions. So now there's one more problem with the simplex algorithm that we need to solve. And so we're going to first discuss what that problem is by looking at this LP. So if this is similar to an LP that we did on simplex day 1, I think it was day 1. Simplex part 1. But I've altered it slightly to give us cleaner solutions that don't have as many decimals in them. I wasn't really happy with that one. So let's do a simplex iteration. So you don't tune out, I've already done the simplex iteration. I've already done the pivot. So I'm not going to be doing anything by hand today. We've done plenty of that, I think. Let's think about what we would pick. 3 b over a be 1, 3.3 repeating, and undefined. So I pick 1 and pivot on that point, which moves us from the origin to this point, 1, 0, to that extreme point. And then we'd pick y. We have a negative, a 1/2, ignore that one, 1 and 4, pivot on that point, which moves us from this extreme point I don't know why some of my annotations don't like to show up. Moves us from that extreme point to this extreme point. So now that we're at that extreme point, let's we can see that we would want to pivot S1, and I think here would be 7, whereas this would be 21. So I think we would pivot on that entry, which should push us up to here, which we discussed was the optimal solution to that similar problem we did in simplex part 1. But instead of that, let's think about what happens if we add a new constraint to the problem right here at this basis. Well, first we're going to add it to the initial problem. We had this new constraint, x less than or equal to 3. And remember, we were at this extreme point a second ago. So we've added a new constraint that that passes through that same extreme point. So remember, I said that an extreme point is the intersection of n hyperplanes. N hyperplanes, where n is the number of decision variables. Here we have an intersection of n plus 1 hyperplanes. And that means, in our case, 3 hyperplanes. But remember that a basis, each basis corresponds to an extreme point. And that may have been a slight overgeneralization, because a basis actually corresponds to a basis corresponds to the intersection of n hyperplanes. And so really I want to come in here and alter this definition a little bit and say an extreme point is the intersection of at least n hyperplanes. So in the case where we have more than n hyperplanes intersecting the same point, it may be that our basis, or that it may be that there are many bases corresponding to our extreme point. So there may be, it's going to be n plus 1, choose n, which is just n plus 1 bases, distinct bases corresponding to the same extreme point. And if there were, say, more constraints, more hyperplanes passing through that same point, we would end up with even more distinct bases corresponding to the same extreme point. So we could have as many as n plus, I'm not going to call it m, I'm going to call it j, choose n. Don't worry about that notation if you're not familiar with it and it's behind my head. Suffice it to say that that is a very big number. And we don't want very big numbers of things. So this is bad, and we'll show you why that's bad coming up. So let's think about a pivot on this basis, or on this tableau. Remember we had our basis was, on the last page, was x, y, and S3. X, y, and S3. So we're going to pivot back into that basis here. But we have another constraint and another slack variable. So we actually have 4 entries in our basis. There should be as many basic variables as there are constraints, excluding non-negativity constraints. So what do we have here? Okay, yes. So let's think about pivoting on this basis. We only have one negative entry here. So we're going to pivot in S1. And then let's go through and get our ratios. We have a 21, a negative 7/3, a 7, and a 0. Remember in the past, we've had zeros in the column, and it's been undefined because you can't divide by 0. But you can have 0 in the numerator. of a ratio. So 0 divided by anything is 0. We haven't really dealt with what happens when we have a 0 over here. Because we have to pick the smallest one. Otherwise, we'll pivot to an infeasible point. So we are going to pivot around that entry. Now here's where things get sticky. Because now we have our new basis xy, s3, s1. But our solution is the same as it was before our pivot. And in fact, our objective function value is the same as it was before our pivot. So we haven't, one of our iterations hasn't actually improved things. And in this problem, or in this LP, that's not really a problem because next we're just going to pivot S4 and it's going to move on from there. Except we still have a 0 there. So I'm wondering how this all works out. But it could be that our simplex gets stuck in an infinite loop of pivoting between what we call degenerate solutions. Degenerate solutions are extreme points. With multiple distinct bases. And pivoting between multiple bases that have the same extreme point doesn't get us anywhere. So let's consider this problem. And we're going to do sort of the same thing. So here's its tableau. We want to pivot on this entry, and notice we have zeros. So our B over A is going to be zeros. And we're going to pick arbitrarily between these two pivots. Let's pick S1 for our sake. So we're going to pivot on that entry. We end up with this tableau. There's our smallest negative, since we are maximizing. Pivot on that one. 2.5. Pivot there, since we still have zeros over here. And then ignore this. That's a numerical error. That is actually 0. That's within the machine precision of my computer. So that's 0. If you want to know more about that, take a numerical, what is it called? Numerical linear algebra class, or a computer science class, or what have you. Um, x3, again, a tie. We're going to pick x1 because we can arbitrarily. We don't have a rule for picking these. X4, pivot out x2, because again we're tying over and over again, tying at 0. And then S1, still tying, pivot out x3. Here we go, -4, pivot out x4. And I'm missing an image, but if you remember, our first tableau for this was in the basis S1, S2. And so we would end up back at the start because our first, we're pivoting into S1, S2. So you would end up right back here, and the cycle could repeat forever. That's not great. That's not what we want. Remember, our book promised us that the simplex algorithm will terminate. What that means is that it takes a finite number of iterations to solve an LP. But this looks like there are instances where we could get stuck cycling through the same degenerate point forever, stuck in an infinite loop. That's a big, big problem. On small problems like this is a relatively easy thing to identify and to work around. And I'm repeating myself here a little bit because this is important to understand that just because we can see a sort of redundant constraint or a degenerate solution in 2D doesn't mean that we can see that easily in 100 dimensions or 100,000 dimensions or what have you. So we need a systematic way of dealing with this problem. And fortunately, there are dozens of ways to deal with this problem. You could randomly pick between ties at 0, and eventually statistical analysis tells us that eventually we would break out of our degenerate solution and continue to improve the problem. You could keep track of the bases that you've swapped into and tell the computer not to swap into any of these bases again. That one works. You could ask the computer to, at every step, at every iteration, every time you want to pick an exiting and an entering variable, you could ask it what pivot will give me the best, the most improvement. What full pivot? Because at the moment we're asking what entering variable gives me the most per unit. But we could ask which pivot gives us the best. That works. It takes a long time to compute, but it works. It's a slow one, so we don't use that one hardly ever. There are various sorts of ways of ordering your variables so that this doesn't happen. And the one that the book presents, which is the one that I'm going to talk about here, is it's called Bland's rule. And this is sort of a footnote in the book because It's not something we have to think about a lot, but it is important to solving some of these problems. It just says that of the variables that have a negative c value, if we're maximizing, if we're minimizing, you would replace it with a positive. We should pick the one with the smallest index to enter the basis. So that would be, say we had variables like we have up top, x1, x2, x3, x4, s1, and s2. And we're just going to order those 1, 2, 3, 4, 5, 6. Those will be our indices. And we will just pick the one with the smallest index if we have multiple options. And then after you've picked your entering variable, if we have a b over a tie, choose the variable with the smallest index again to leave the basis. So let's go back up here somewhere. I'm trying to remember where exactly this one breaks down. Where we did a bad thing. Yeah, well, at the first step, we pivoted out S2, which has a higher index than X1. So that one is a mistake. Here we pivot out X3 when we could have, well, no, that's not a mistake. Yeah, so that's our only mistake. But that would have sort of a trickle-down effect. And ultimately we would find out that this problem is unbounded, but it actually, well, this is not a great example, but it was the first one I found. This one is actually only has one solution. So the point is kind of moot here, but this problem can exist on bigger sorts of things. So I think that took far less time than I was expecting it to, so I think what I'll do is do another example myself using a program to do my pivots, and we'll look at it together just to take up a little more time and give us some more exposure to this concept and how it works. So the book says that the simplex algorithm, if we use Bland's rule for selecting pivots, the simplex algorithm terminates in a finite number of iterations. And that's always true. That's been proved. It's widely accepted. Bland's rule is one of the more common ways of dealing with degenerate cycles in our LPs. So let me take 1 second and pull up my program that will let me do some more pivots. And let me grab this book behind me. And we're going to look at another example. Okay. Hmm. Here we go. I'm going to grab this. Okay, I've got those defined. So this is a program I wrote to do pivots and print tableaus for me in Mathematica. So this problem is a minimization problem. Its objective is negative 3/4. I apologize that this is taking some setup time. I was expecting the proper lecture to take longer, but we have so much time that I don't want to waste. This should have a x1 plus. And that's that. Let me get my Tableau print. Here we go. There's our tableau. Finally. And remember that we're minimizing here. So we're actually going to pick the largest positive number. Which means that we want to pivot on x4, and we're tying, so let's ignore Bland's rule for now. And, well, I guess we are pivoting on x1. So x4 replaces x1. Great. Pick our largest, and then we're going to pivot on x2, so x5. It's going to replace x2. And then our only positive left is x6. Going to pivot on x4. So x6 replaces x4. And then we have another positive. We have two positives. But because we're ignoring Bland's rule, we're going to pivot on x7 because it's the biggest. And x5. So x7 replaces x5. We only have one positive here. And we're going to pivot x1 into x6. So now we have two positives again. Pick the biggest one and pivot on x2 into x7. And suddenly, you'll see we're back. x1, 2, 3, x1, 2, 3. We're back in the same basis that we started from. So we've cycled. And this could happen forever. This is unlikely to happen it's very unlikely to happen in small problems like this. But as your problem becomes larger, and as the problem becomes more sparse, by which I mean that its A matrix has more and more zeros in it, it becomes more and more common. So things like set partitions, vertex matchings, a lot of graph theory related problems turn out to be to have infinite cycles like this in them. So what happens then if we do Bland's rule instead? Well, let's see. Let me copy this. So we have 1, 2, 3. And I think this book says that the first 4 tableaus are the same. So let's verify that. We end up with so picking Bland's rule, we have two positives. We're going to pick the one with the smallest index, i.e. 4 is smaller than 6, so we pick x4. And then we have two ties at 0. So we pick the one with the smallest index, x1, and pivot. Oh, I forgot to. There we go. Pivot. It was x4 in, just like we did previously. Here we only have one no, we have two positives, but 5 is still the smallest index. So pivot on 5. We have another tie here, so we pick x2, just like we did last time. Again, only one positive. Two ties at 0. Pick the smallest index. 6 replaces 4. One, two, three, four. So maybe we'll see a difference here. Yeah, so last time we pivoted on x7 because it had the largest positive entry. But we see that x1 has also a positive entry and a much smaller index. So we're going to pivot on x1. I want to make sure I'm doing this correctly. Pivot on x1. Yeah. In the fourth tableau, x1 and x7 are eligible on the basis. x1 enters the leaving variable because we have another 0, 0 tie is x5. Also, this is negative, and we typically don't want to pivot on negative values because remember they indicate that there might be an unbounded sort of solution. So we pick x5, and we're finally doing something different. So x1 replaces x5. We have two positives. Pick x2. And I think we have, these two are negative, so we ignore those and pivot on x3. I think. Let's try this. So x2 replaces x3. What do we have? It's still feasible. Great. And we have a non-zero thing. So I think we're out of the degenerate cycle. Yeah. Great. So pivot on x4. This is going to be 4. This is 1. 0 is undefined. So pivot on x2. x4 replaces x2. there we go. We have an optimal solution. So Bland's rule works. It's been proven to work mathematically. It's been widely accepted. I think most commercial solvers use Bland's rule or a slight alteration called the lexicographic rule. That's more complicated, but a little bit faster. So that is how we deal with degenerate cycles, the problem of degeneracy, the problem of redundant constraints. A simple solution, but an important thing to understand because the simplex algorithm, we've been using it like it just works, but sometimes we have to be a little smarter about it. Anyway, that is all I wanted to talk about today. So we get a short lecture on the halfway mark. I'll stick around for a little bit in case anyone had any questions. But you guys are free to go.